Welcome to the AI podcast. I'm Daniel, and with me is Maya. Today we're unpacking Toolformer, a research paper from Meta AI that asks a simple question with a big punchline. Can a language model teach itself when to use external tools like a calculator or a search API?
Hi, Daniel. I skimmed the abstract earlier and it sounded almost too neat. What's the quick takeaway?
Here's the TLDR up front. Toolformer shows that a general-purpose language model can learn, with only a handful of human examples per tool, to decide on its own when to call small external tools. That self-taught tool used noticeably improves things like factual accuracy, basic math, and time-aware answers. And it does so without hurting the model's writing fluency.
So give the model a calculator and a search bar and let it figure out when to tap them. Got it.
Exactly. The work was led by Timo Schick at Meta AI, with colleagues including Dwivedi-Yu and Zettlemoyer. It first appeared on AR-Chev in early 2023 and was later presented at NeurIPS.
Before we dive into the mechanics, what pain points are they trying to solve?
Big language models are impressive storytellers, but they still hallucinate facts. They're shaky on arithmetic, and they lose track of what day it is. A common fix is to bolt on tools like web search or a calculator, but prior systems usually needed lots of hand-labeled demonstrations, or they hardwired task-specific pipelines. That makes them brittle and expensive to adapt.
Right, and those pipelines don't feel like general intelligence. They're more like carefully staged demos.
Exactly. The gap this paper tackles is how to keep the model general and flexible, yet still let it reach for tools when that would actually help.
All right, walk me through the idea. How does a model teach itself to use tools?
The method has a clean loop. First, you give the base model a few simple demonstrations showing how an API call is written in text. Then you feed the model ordinary text and ask it to propose spots where a tool might help. It proposes a call, you execute the real tool, paste the tool's answer back into the text, and check whether that extra snippet makes the model's next word prediction measurably better. If it helps, you keep that example. If it doesn't, you discard it. Finally, you fine-tune the model on this filtered, tool-augmented text so it internalizes when and how to call the tool.
So the model isn't rewarded for calling tools in general, only for calls that actually improve its predictions in context.
Exactly. The filtering step is the key. It's a self-supervised signal. Did this call reduce the model's uncertainty about the next words? If yes, learn from it. If not, ignore it.
And at inference time, what happens? Does the model ask permission to call a tool?
In practice, the fine-tuned model emits a special token when it decides a tool would help. The system pauses, runs the tool with the arguments the model suggested, inserts the tool's output, and then the model continues generating from there.
Nice. What tools did they actually use?
A small toolkit, a basic calculator, a Wikipedia-style search, an external question answering system, a machine translation model, and a simple calendar that returns today's date. The base model they trained was around 7 billion parameters in the GPT-J family.
Let's talk experiments. How did they test whether this really works?
They kept things honest and general. Everything was zero shot, with no example answers in the prompt at test time. They also limited the model to at most one API call per input to avoid runaway tool calling, and they measured language model fluency to make sure tool training didn't hurt writing quality. Comparisons included the same base model without tools, the tool-trained model with tools switched off, and larger baseline models. They covered factual recall, math word problems, open domain QA, multilingual questions, and time-sensitive queries.
Quick clarification. If they have a QA tool, couldn't the model cheat on QA benchmarks by outsourcing the whole job?
Good catch, and they accounted for that. On open domain QA benchmarks, they disabled the QA tool and only allowed simple search, so the model had to piece things together. Conversely, on certain factual recall tests pulled from Wikipedia, they avoided letting the model search Wikipedia. The idea was to show principled gains, not shortcuts.
That's reassuring. So what changed with tools available?
3 headline effects. First, math got better. With the calculator available, accuracy on word problems rose compared with the same model without tools. Second, factual questions benefited. The model could check names and dates more reliably. Third, temporal awareness improved. With access to the current date, it stopped guessing about what day it is. Importantly, the model's writing fluency stayed essentially unchanged.
That last point matters a lot. There's always a worry that narrow training harms the model's voice. So, in plain language, it writes just as smoothly as before, but now it knows when to look things up or calculate.
Exactly.
Were there any areas where the gains were modest?
Open domain QA with only a basic search tool saw improvements, but didn't leapfrog the largest baselines. That makes sense. The search was non-interactive, and they allowed only one call per question. Complex questions often need iterative browsing or multiple hops, and Toolformer in this paper doesn't do that.
Understood. Let's zoom in on the design choices a bit more. You mentioned one call per input. Why that constraint?
Mostly to keep training and evaluation simple and to avoid unpredictable loops. It also highlights a real limitation. Without multi-step planning, the model can't chain tools. For example, it can't ask for today's date, then feed that into a search query, and then check a calculation. It has to pick the single most helpful call.
And how did they decide where to try calls during training? Randomly?
Not quite. They steered the sampling a little. For instance, if a passage contains several numbers, it's a promising spot to try a calculator call. But the final arbiter is still the usefulness filter. If adding the tool result doesn't help prediction, the example is thrown away.
That suggests another challenge. If only a small fraction of proposed calls help, you have to sift through a lot of text to harvest good training traces.
Exactly. For some tools, like the calculator, the yield can be low. That's a sample efficiency issue, and it's one reason future work might do iterative bootstrapping to improve the hit rate.
Reproducibility is always a question with these systems. How accessible is this setup for other labs?
The paper describes the components and hyperparameters clearly, but reproducing the full pipeline still takes serious engineering. You need working tool backends, the filtering process, large-scale text processing, and a fine-tuning setup. Community reimplementations exist, but it's not a one-afternoon project.
Makes sense. I'm also curious about scaling. Does tool use only help smaller models, or is it still useful when models get bigger?
The study suggests tool use is helpful across sizes. Very small models struggle to orchestrate tools, but once you reach mid-scale, the model starts using them effectively. And even larger models still benefit from calculators and lookups because precise arithmetic and up-to-date facts are hard to memorize.
All right, let's take stock. What, in your view, is the core contribution?
A simple general recipe for teaching a language model to use tools without heavy supervision. Instead of hand-labeling when to call a calculator or search, the model proposes calls. You keep only the ones that measurably help prediction, and you fine-tune on that. The result is a generalist writer that can also be a careful checker.
And the fine print?
A few caveats. No multi-step planning or tool chaining in this setup. The search tool is basic, with no browsing or query reformulation. Tool calling decisions can be sensitive to prompt phrasing and decoding settings. And the data generation stage can be compute hungry because many proposed calls won't pass the usefulness filter.
Still, the direction is exciting. It feels like a bridge between classic language modeling and the newer wave of agent-style systems.
I agree, and it points toward clear next steps. Enable multiple calls so the model can plan short sequences, add interactive search and light browsing. Make the model cost-aware so it calls tools only when the benefit is likely. Improve robustness so tool decisions aren't brittle, and broaden the toolkit to include things like code execution and structured retrieval.
If I imagine a future version, it might handle a question like the inflation-adjusted cost of something in today's dollars by grabbing today's date, fetching the relevant index, doing the math, and then explaining the path it took.
Exactly. That's the spirit of tool chaining. Toolformer shows that the first step, learning when a tool helps, can be taught with minimal human oversight. The natural evolution is to connect steps and verify results along the way.
All right, last question. For listeners who want a mental picture, how should they visualize what Toolformer learned?
Picture a writer with a few light instruments on the desk: a calculator, a search box, a translator, a small date stamp. While writing, they occasionally pause and think, A quick lookup would reduce guesswork here. They reach for the right instrument, jot the result into the draft, and keep going. The tone and style stay the same, but the answers are steadier.
That's a helpful image. So, to wrap up, Toolformer's message is that general-purpose language models can become more reliable not by memorizing more, but by learning to ask for help at the right moment.
Well said, and that's our episode on Toolformer. If you enjoyed this breakdown and want us to cover related work on multi-step tool use or agent frameworks, let us know. Thanks for listening.
Thanks, everyone. See you next time.